I've just finished this sandcastle, and unfortunately, its demise is imminent.
The tide is coming back in, so the clock is ticking. But what exactly are tides, and what causes them? And why do they hate sandcastles so much? Let's find out together in this episode all about tides.
Before we can figure out what's going on with the movement of the ocean, we need to take a look at a force that is always at work here on Earth and even out in space: gravity. Gravity is the attractive force between all objects that have mass, and gravity is the force that creates tides. Newton's law of universal gravitation tells us that the greater the mass of the objects and the closer they are to each other, the greater the gravitational attraction between them. Sir Isaac Newton explained that the ocean tides result in the gravitational attraction of the sun and moon on the Earth. So gravity weakens with distance, and this change of gravity over distance is known as tidal force. Let's break this down and simplify things a bit. Let's say we have one massive object that is affecting another object with its gravity. Its tidal force depends on the answer to these three questions. What is the mass of the first object? Basically, how strong is the gravitational force of the first object? The more mass equals the stronger the force of gravity, which equals a stronger tidal force on the affected object. 2. How far is the affected object from the first object? We learned that gravity weakens with distance, so the farther away the affected object is, the lower the tidal force will be. Less gravity equals less tidal force. 3. How wide is the affected object? The wider the object is, the more the force of gravity from the first object changes as it moves across it, and so the bigger the tidal force.
This tidal force is what occurs between the Earth and the Moon. If you aren't yet familiar with the phases of the Moon and its relation to the Earth, you can check out this episode.
We know the Moon orbits around the Earth, while the Earth is simultaneously rotating and it's also orbiting the Sun. The attractive force from the Moon is pulling on the part of the Earth that is facing the Moon.
Let's use this giant stress ball to model what's happening to the Earth. The Moon is applying a stronger force to one end of the Earth than the other, so let's pull on one end. The side of the Earth that is facing the Moon is pulled more by the Moon than the other side, so the Earth stretches toward the Moon.
Here, we are going to look at the side of the Earth closest to the Moon, the center of the Earth, and the side of the Earth facing away from the Moon. Gravity is measured from the center of objects. This means that the side of the Earth facing the Moon feels a stronger pull toward the Moon than the center of the Earth. And the side facing away from the Moon feels an even weaker force toward the Moon than the Earth's center. But gravity is affecting all of the Earth, so it's also pulling on the top and bottom, which looks more like this, a pull that is simply more inward. More on that in a bit.
Therefore, the tidal force is the strongest on the side of the Earth that is facing toward the Moon and away from the Moon, and weakest in between. If you're still here, liking this video, let us know, and hit that subscribe button so you never miss an episode. Most of the Earth is covered in water, and water responds to this stretching more so than the solid Earth.
Remember from earlier that the pull from the Moon isn't the same across the Earth. Because of the distance dependence of gravity, the part of the Earth closest to the Moon has a greater pull toward the Moon. The parts of the Earth here are pulled in more of an inward angle, and the far side has a weaker pull. And because our planet is basically a rock covered with a thin layer of gases and water over most of its surface, those fluids are affected by this pull in a greater way. Gravity is where it all begins, but it's important to quickly look at a force working with gravity creating tides. We know that solids and liquids have very different properties, and their ability to transfer energy or pressure is what we're looking at. Because the pull of the Moon here at the top and bottom of the Earth in our simplified example is more inward, the water in these areas are bumping into their neighbor. This water is being pulled into this neighbor by the lunar gravitational attraction. This is where the pull also becomes a push. So this guy is pushing and transferring pressure to its neighbor, and this continues until enough pressure builds, causing the tidal rising of the ocean, forming a bulge.
You might expect just one bulge here on the side of the Earth that is facing the moon, but that's not the case. You can also see this modeled again here with our stress ball.
The Earth is not only being pulled by the moon, we now know that the same pull turns into a bit of a push on the oceans. The water here is also being pushed in this direction, which contributes to a second bulge here at the opposite end.
These bulges of water create tides. Tides are the regular rise and fall of the ocean water levels. You may have thought that the ocean moves in and out, but more accurately, the Earth moves in and out of the oceans. Rotate with me as we observe the Earth's tides. As the Earth rotates, the water bulges stay in line with the moon, while the planet's surface moves underneath it. Let's say we are here. When our location is in the area of a bulge, it experiences a high tide. And as we travel, when our location reaches a valley, it experiences a low tide. If we complete one planetary rotation, or one day, our specific location will pass through both bulges and both valleys. It feels like we're forgetting about a pretty big object in our solar system. What about the sun? The sun's location in relation to the moon alters the strength of the pull on the ocean. Let's make this a tad more complicated. The sun is even bigger than the moon. Understatement of the year. Remember, the greater the mass of the objects and the closer they are to each other, the greater the gravitational attraction between them.
So even though the sun is far more massive than the moon, it's much farther away.
This means that the sun's tidal force ends up being about half that of the moon's. How the sun affects the tides depends on its arrangement with the Earth and the moon.
When the Earth, the sun, and the moon are all lined up, the gravity of the moon and the sun add up, resulting in higher high tides and lower low tides, called spring tides. This happens when the moon is either on the same side of the Earth as the sun, new moon, or directly on the opposite side of Earth, full moon. Smaller than usual tidal ranges, called Neap tides, occur when the sun and the moon are at a 90-degree angle to each other relative to the Earth. During first and third quarter phases, the gravitational forces are not aligned, and high tide from the moon overlaps low tide from the sun. This results in a slightly lower high tide and a slightly higher low tide.
So the next time your sandcastle gets obliterated by the ocean, don't shake your fist at the waves because, after all, your sandcastle spun into the ocean, basically. And if you want to learn more science, you can check out this video next. Hey! Hey! You got a fan club.
Oh, no, sir.